All right, calculus students. Hey, how are ya? We are continuing with Unit 10, Infinite Sequences and Series, and today is Lesson 4, Conditional and Absolute Convergence. So we are still looking for those rules. Does it converge? Does it diverge? Inside that convergence category is a subset. When we're looking at something called alternating series, and we'll actually look at those first, you can look at alternating series and decide if they converge absolutely or if they converge conditionally. It's just putting more classification on the type of convergence that you could have with a series. So we're going to look at a series that have positive and negative terms. This is called an alternating series, is a series whose consecutive terms alternate between positive and negative. They just flip-flop, positive, negative, positive, negative. We have a series that's absolutely convergent if the absolute value of that series is convergent. It seems like it's obvious, but it isn't necessarily. We'll look at a few examples of that. The first example that I have is 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared. So first it's alternating because those signs go plus, minus, plus, minus, plus, minus. But it converges absolutely because if I look at the absolute value, all positive terms, 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, those converge by something called the p-test. And I know I talked about that a lot in the last lesson, so there's your p-test. My conditional convergence happens if I have an alternating series converge, but if the absolute value version of it diverges, then we call it conditionally convergent. The biggest example I can kind of give you of that is 1 over n. So if I switch, if I did 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5, when it's alternating, it would technically converge because it goes back and forth, and each term is getting smaller. However, if you looked at the absolute value, meaning always positive, this one would diverge. And so I know it diverges because this would diverge by the p-test. So if the alternating piece, I spelled diverge, no, diverge is good. If the alternating piece converges, but the always positive, the absolute value piece diverges, then we call it conditionally convergent. I know, it's crazy. So alternating series test. This one is probably my second favorite after the p-test. That p-test we use a whole lot. The alternating series test is a really good thing. If you have a series that is decreasing or a sequence that is decreasing and those terms are getting to 0, then this looks funny. The summation from 1 to infinity of -1 to the n minus 1, a sub n converges. If you have decreasing terms and those terms converge to 0, when they alternate, it is converging. Now, a couple ways to write alternating. You can have -1 to the n minus 1, which they've listed here. You can have -1 to the n, also fine. You can have -1 to the n plus 1. And then this one's a little different. I've seen sine of pi n. I gotta think about that for a second. Sine of 0 is 0. Sine of 1 pi is 0. I guess it's cosine. I think that's right. So cosine of pi is 1. Cosine of 0 is 1. Sorry, it's been a long day. Cosine of pi is -1. Cosine of 2 pi is 1. All right, that one alternates between positive and -1. So just, be on the lookout for that. Those trig functions can sneak in there. So here's example 1. I have -1 to the n over natural log of n. So we want to say, does, the question's not really here. Does the series converge absolutely? Does that series converge absolutely? So what we're going to do is look at the original. This is -1 to the n natural log of n. So this piece in the numerator, that's what makes it alternating. Then look at the rest of it. Look at 1 over n natural log. I wrote 2, that should be an n. Natural log of n. Are those terms getting smaller, getting to 0? Yeah, they are. Are they decreasing? Yes, they are. So because these are decreasing, check, there's my decreasing. Converge to 0, converge to 0, check. I mean, think of 1 over 100, natural log of 100. Yeah, that's gonna be a really small fraction. This one converges by alternating series test. So again, alternating series test, really nice one. And then you want to look at the absolute value of it. So you want to know if the whole positive version, if those converge. So let's check just the positive version here. So if I look at n equals 2 to infinity, 1 over n ln of n. I keep writing 2, ln of n. I'm going to use the integral test. I see an integral in there. So I'm going to rewrite this. 1 over x, natural log of x dx. The limit as r approaches infinity. Here's my infinity, here's my 2. I would say that u is the natural log of x. Du is the derivative of that, which is 1 over x dx. So this would become du over u. Limit as r approaches infinity. This should be an r on the top, from 2 to r. This is a du. I already have the du. It's currently 9:30 at night, so yeah, a little sleepy here. So this would become the limit as r approaches infinity of the natural log of u between 2 and r, natural log of r minus the natural log of 2. If I put the limit as r approaches 0, nope, r approaches infinity. So this is infinity minus natural log of 2. This is infinity. This diverges. So because the original converges by the alternating series test, but the absolute value diverges by the integral test, we say that this is conditionally convergent. Conditionally convergent. What's conditionally convergent? The original. -1 to the n ln of n. All right. All right. This isn't too bad once you get the hang of it, but you do have to try a few. Example 2, show that this is conditionally convergent and S is between 0 and 1. What do I mean by that? I've got to cheat with my notes here. Okay, so let's look at the original one. N equals 1 to infinity, -1 to the n minus 1 over the square root of n. So this tells me that it's alternating. And then you want to look at 1 over the square root of n. Are these decreasing? Yep, those are decreasing. Will they go to 0? 10 to 0. Yep, the larger that n gets, the closer you get to 0. So this one is going to converge by alternating series test. And that's the thing about these. You have to justify. You have to be able to say what test you're using. And then if I switch and look at that always positive version, the absolute value, I've got 1 over the square root of n. And if we rewrite that, 1 over n to the 1/2, what test can we use? P-test. Does this converge or diverge by p-test? Diverges by p-test. because that 1/2 is less than 1. So we know that it diverges. So what does that mean for the original? It means that the original is conditionally convergent. Square root of n is conditionally convergent. Show that s is between 0 and 1. Hold that thought. And the s is between 0 and 1, the partial sum. So I have a picture of it here. Well, if you start with n equals 1, right? This would be 1 over the square root of 1. And if you have n equals 2, that would be -1 over the square root of 2, plus 1 over the square root of 3, minus 1 over the square root of 4. So basically, this number is as large as it gets. You get to 1. And then if you keep going, and going, let's do 100. So it'd be negative square root of 100. That's pretty small. That's almost 0. And if you keep going with like 1,000, that's really, really close to 0. So it's not in your notes here, but it's in my old section of notes. There's a picture. This is lousy. There you go. But you can see that your sums are alternating. They keep going up and down and up and down and up and down. So you start at 1, down to -1, and they keep going and getting closer and closer to 0 because you're adding a positive 1 and then you're subtracting a 0.9. And you're adding a 0.8 and you're subtracting a 0.7 as they get closer and closer to 0. So that one might trick your brain a little bit. All right, one more example and then we're finished. Actually, this was the example I gave you at the beginning. Show that this is conditionally convergent. So the piece on the top, this is how I know it's alternating. When you see that -1 to the end, that's your clue that it's alternating. So if you look at the rest, 1 over n decreases. As n gets larger, that decreases. And it tends to 0. If you put infinity in for n, you're going to be close to 0. So this original one converges by alternating series. And again, you just want to like further clarify, well, what kind of converging do we have? Do we have absolute convergence or do we have conditional convergence? So you have converge and diverge, and then your converge can be broken into conditional and absolute when you're talking about alternating series. This is crazy. Draw yourself a picture if you need to. So then look at the always positive one, 1 over n. And we actually talked about this 2 lessons ago. This one, you can use the p-test. And if this exponent is a 1, it diverges. You also have a second one, and some students always feel a little bit more comfortable with this. And this is 1 over x dx between 1 and r, the limit as r approaches infinity, integral test. This is the natural log of r minus the natural log of 1, the limit as r approaches infinity. This is going to be infinity. This diverges. So we know that it diverges, the absolute value piece. So this is conditionally convergent. So not only does it converge that original one, but it's conditionally convergent instead of absolutely convergent. Conditionally convergent. All right, so I will be perfectly honest. It took me 3 or 4 classes, 5 classes to teach this over and over and over again for this to really sink in. So be patient with yourself. Converge, diverge. Converge can be conditional or absolute. All right. Make sure you're asking questions to both myself and Mrs. Oakes. Bye, guys.